All right, let's look at some questions that put it all together from the entire module right now. And when you're going through these, I think it's best to pause the video, work the problem out, and then see if your answer matches up with mine. I also think it's a great idea to have those decision trees out, and that way you can kind of structure your thinking as you're going through this. So number one, according to the National Health Statistics reports, a sample of 360 one-year-old baby boys in the United States had a mean weight of 25.5 pounds, and we can assume that the population standard deviation is sigma is equal to 5.3 pounds. Part A, construct a 95% confidence interval for the mean weight of all one-year-old baby boys in the United States. So that tells me, if I have that decision tree out, that I'm going to be working with means, and the next box on that decision tree is a quick check to see if we can use that distribution of sample means. And as we look up here, let's see, we have a sample size of 360, and so that's clearly bigger than 30. And then as we continue on the decision tree, we see that we are given sigma, the population standard deviation. And so I know that I'm going to be using z-interval in this question. And so we can go into stat, tests, and then z-interval is number 7. And let's enter the standard deviation of 5.3. We'll go down to x bar, that's our sample mean, and our sample mean is 25.5. And then we go down to the sample size, and that was 360. The confidence level is 95%, so we can press calculate, and we end up with a confidence interval of 24.953 up to 26.047. Part B, based on that confidence interval constructed in Part A, is it likely that the mean weight of all one-year-old boys is less than 28 pounds? So what is very likely, what we have 95% confidence in, is that the mean weight is between about 24.9 and 26 pounds. And so if that's the case, then is it likely that the mean weight is less than 28 pounds? Absolutely. So the answer to this question would be yes. Okay, let's go down to question 2. In number 2, this says, in a simple random sample of 100 electronic components produced by a certain method, the mean lifetime was 125 hours. Assume the component lifetimes are normally distributed with population standard deviation sigma is equal to 20 hours. Okay, it says find the sample size needed so that a 99% confidence interval will have a margin of error of 3. And so this is probably the toughest question in this entire module, because we have that formula that we have to work with, that sample size formula. So we know it's going to have to be n is equal to, it's going to be z alpha divided by 2 times sigma divided by m, the margin of error, and then we're going to square that. And so we have m, the margin of error. We're told that that margin of error is going to be 3. So m is equal to 3. Sigma is equal to 20. And the only thing that we really have to find here is z alpha divided by 2. So let's do that. So to find z alpha divided by 2, this is where we set 1 minus alpha equal to the confidence level. That implies alpha will be 0.01. So I am looking for z of 0.01 divided by 2, which is z of 0.005. You can confirm that over here. 0.01 divided by 2, you can see 0.005. And this is the z-score for which the area to the right is 0.005. Now we talked earlier about how we can approach this. Since we're looking for a z-score for which the area to the right, this area to the right of our z-score is going to be 0.005, then the area to the left of our z-score is going to be inverse norm, and it's going to be 1 minus 0.005, comma 0, comma 1. And so we end up with, let's go inverse norm, second vars. I That should do second vars. There we go. Inverse norm is number 3. And we're going to say 1 minus 0.005. We can let the calculator do all the calculating. We don't have to actually compute that and then enter it in. The mean is 0. The standard deviation is 1. We paste and press enter, and we get a z-score of 2.5758, etc. So this is our z alpha divided by 2. So now what we're going to do is we're just going to substitute this in to this formula, multiply it by sigma, divide by m, and then square that entire thing. So I'm going to do it like this. I'm going to say answer multiplied by sigma, and my sigma is 20, divided by the desired margin of error of 3, and then we're going to square that entire thing. And we end up with 294.88. And recall that when we're doing these problems, we always round up to the next whole number. So the solution to this question is going to be 295. That is our best answer to this question. Okay, let's move on to question 3. So in question 3, this says, in a sample of 123 hip surgeries of a certain type, the average surgery time was 136.9 minutes. So that looks like it's our sample mean, and a standard deviation of 22.6 minutes. Notice they give us a standard deviation here, but they do not say that sigma is equal to 22.6. So when they're talking about 136.9 and the 22.6, they're actually referencing a sample. And so this is really important because when we're doing a confidence interval for the mean, and you're pulling that decision tree out, and you're on that mean track, and you see that our sample size was at least 30, you get to the point where you have to decide, is sigma given or not? You would have to say sigma is not given. S is given. We see that S, our sample standard deviation, is 22.6. And so because of that, we are going to use t-interval, and then we can put our numbers into the calculator. So let's say stat, test, t-interval is number 8, and you can see that our sample mean we are going to enter is the average surgery time of 136.9. Our sample standard deviation we just said was 22.6, and our sample size was 123. We do want a 95% confidence interval. We calculate, and our interval is 132.87 up to 140.93. Part B, if a 99% confidence interval were constructed with these data, would it be wider or narrower than the interval constructed in Part A? Now, I'm hoping that you could think about this and you know that answer without even generating that 99% confidence interval in the calculator, but you can confirm it in the calculator. But if you're going to have more confidence that the true population mean is going to be in your interval, then the only way to have more confidence is to have a wider interval. So it's going to be wider, but let's confirm that. So we'll go back to stat, tests, go down to number 8, and this time we are going to change the C level to 99. We press calculate, and we can confirm that we get a wider interval. We can see that our interval becomes 131.57 up to 142.23. Okay, one more question here. So we have this sleep apnea question. Sleep apnea is a disorder in which there are pauses in breathing during sleep. People with this condition must wake up frequently to breathe. In a sample of 427 people, so there's our sample size, there's our N, aged 65 and over, 104 of them had the certain characteristic of sleep apnea. So 104 is going to be a key part of this also. Part A says find a point estimate for the population proportion of those aged 65 and over who have sleep apnea. So if you're using a point estimate, then you just have to use the results from your sample. The results from the sample would suggest that 104 out of the 427 people have sleep apnea. So if we're just using the sample to speak for the population, then we would have to use that point. And so if we do 104 divided by 427, we get an answer of 0.2436 if we go to 4 decimal places, 0.2436. Okay, so now we're going to do a little bit better than that point estimate. We're going to construct a 99% confidence interval for the proportion of those age 65 and older or over who have sleep apnea. So since we're doing a confidence interval, you pull that decision tree out and you ask yourself, are you doing a confidence interval for means or proportions? And you clearly see that we're doing this for a proportion here. And so we would be on the bottom track of that decision tree, on the proportions track. And we see that it's taking us to the tool 1prop zint. So let's press stat, go to tests, and we're going to go to A. So let's scroll down. There we go, 1prop zint. And we have to enter in our x, which is always the number it's usually the smaller of the couple numbers given in these types of problems. It's the number of people who are exhibiting the certain characteristic of interest in the problem. So that's 104. And n is always the bigger number. It's always the sample size. So we enter an n of 427. We do want a 99% confidence interval. We press calculate, and we get an interval of 0.19005 all the way up to 0.29706. So that's a pretty wide interval, but it is a 99% confidence interval, and so typically those are the widest intervals. So in another study, researchers concluded that more than 9% of elderly people have sleep apnea. Based on the confidence interval, does it appear that more than 9% of people age 65 and over have sleep apnea? Well, based upon the confidence interval, we have a 99% level of confidence that the proportion of people in the population with sleep apnea is between 19 and 30%. And so, does it appear that more than 9% of people have sleep apnea? Absolutely. You would say yes, and the explanation would be that the entire confidence interval includes proportions greater than 9%. So hopefully this helps. And now I suggest just tackling that homework. Good luck.